A vector is a quantity that has both magnitude or length and direction and is represented by a directed segment. You have a new notation here. It almost looks like a ray, but it's not. You'll notice it just has a little thing above it. It's not a little double-headed arrow. It's just one-sided arrow, sort of, so to speak. It can be represented by one lowercase or two uppercase. So we have the lowercase letter V with the little arrow thing above it, right? Or we have the AB uppercase with the arrow above it. Not really a double arrow, just that little single vector notation. A is the initial point, B is the end point. It is important because it has length, magnitude, and direction. So direction matters, meaning the vector AB is not the same as the vector BA. So you can think of it like a ray because direction does matter and order does matter. All right. Magnitude then would be the distance between A and B. That's the length. Direction, that is the degree from horizontal here. So the degree from horizontal. And so you'll notice the direction here is like X degrees. You'll use vectors when you're talking about like plane travel, boat travel, like they'll use vectors to describe degree and how they're traveling, what direction they're traveling in. A vector in standard position has its initial point at the origin. So in the diagram CD, it is in standard position and can be represented by the ordered pair 4, 2. Now you notice I kind of gave you this notation a little bit when we did translations, right? And so I said it can also be represented by these little pointed looking parentheses. Those are your vector. Those are your directionals for your vector. And so if it's in standard position, you assume you start at C, you move 4 places to the right, 2 places up, and that is your ending point of your vector, okay? And so that's what this represents. Think of it like a translation. If I were to translate the origin over to D, that's how I would move it, left 4 and up 2. A vector can be drawn anywhere in the coordinate plane. To write such a vector as an ordered pair, find the change in the x values and the change in the y values, change in x, change in y, from the tip of the tail of the directed segment. The ordered pair representation of the vector is called component form of a vector. All right? So look at the example 1 here. Find the change in x values and the corresponding change in y values, all right? And so this particular one is the vector EF. You start at the point 1, 5. You end at the point 7, 4. So order matters. We're talking about not just length here. So if it were length, then I were doing like my formula for distance. It doesn't matter which one's the first point and which one's the last point, right? Because when I subtract and square it, it's all the same thing. But since direction matters with a vector, you literally have a starting value, E, and an ending value, F. And so you are going to take your ending values and subtract your starting values, all right, to get this information for this particular vector. All right, so for this one, I would say the composite form of this would look like my starting x minus my ending x, and my ending x minus my starting x, and my ending y minus my starting y. Order matters, okay? So I have to start with F, that's 7 and 4, and subtract my E, 1 and 5. And so for this particular vector, it would look like this. 6, negative 1. 6, negative 1. All right. Magnitude and direction are not changed by the translation. All right. Magnitude and direction are not changed. What do they mean? Well, if I were to take this coordinate plane and I were going to go to 6, negative 1, I would be right here. All right. And if I were to draw this vector like that, right? You'll notice that the direction of the vector and the length of the vector did not change. Where it is positioned on my coordinate plane did, okay? But the length and the direction did not change. The purple vector that I drew right here is the exact same length and the exact same direction as the original one. So this still represents the direction and the length of that vector. It does not represent starting point, but it does represent direction and length of the vector. So to start out with, we're going to use our distance formula here. Distance equals x2 minus x1 squared, y2 minus y1 squared. We've used this a million times, right? And so for this, I'm literally just finding length, magnitude, okay? And so I'm going to plug these guys in and solve. So my magnitude, which is represented PQ with my little notation, absolute value, is going to look like this. I'm going to say -4 minus 3 squared plus 2 minus 8 squared. All right. -4 minus 3 gives me what? Squared gives me, 49. And then 2 minus 8 gives me squared. 36. All right. And so I get 85, square root of 85. And when they plug that in, they actually put that into a calculator, 9.2. All right, so that would be my magnitude. Magnitude's easy. They're just asking for length. That's all they're asking for. Now let's look at how do we find direction. Now you'll notice they sketched a right triangle here. All right, so what they did is they have this here, and they started at the starting point, and they just moved how you would move to get to it, okay? So they moved across, and they moved down to get here, all right? And so how far across did they move? They moved from 3 to -4. How far across did they move? 7. They moved 7, okay? And so that's going to go for that length right there. This is going to be 7, all right? And how far down did they go? They went from 8 down to 2. So how far down did they go? They went 6, all right? So that's that length there, all right? And I want to find my angle. So I want to find the angle that it moved from, and I'm talking where it moved from, starting point, the angle compared to the horizontal. So I'm looking for that angle right there. If I were to label, now this is a right triangle, right? This is a right triangle. If I were to label this guy, this is my hypotenuse. Hypotenuse is easy. That's this one right here. Based on this angle, what is my 7? Adjacent or opposite? It's adjacent. So then what is my 6? Opposite. If I want to find that angle, there is a trig function that helps me find that angle. You just thought trig functions were gone. They are still here. Yes. All right. What trig function deals with opposite and adjacent? So the tangent of that angle P should be my opposite over my adjacent. What function do I use when I am looking for the angle? Yes, the arctangent, the inverse tangent. So I would say in my calculators, I would do something like this. All right? And you get approximately 40.6. Now, here's the deal. I am going all the way, so we are talking about starting here and getting there, okay? So bear with me. If I have this triangle that I just solved for, so I just solved for this triangle right here, right? I'm just bringing him out. And I solved for this piece of it, and I got that it was 40.6 by using my trig information. When I'm talking about a vector, I'm talking about it going from the horizontal. So in my movement, I'm talking about starting here. So I have to go all the way here first before I can move 40.6 degrees to get to my final destination. I have moved half a circle. How much have I moved? 180 degrees. So the final movement of this is actually going to be 180 degrees plus the 40.6. Why? Well, because if I just say 40.6 and everyone knows it's from my horizontal, where is 40.6 going to be? Well, 40.6 is going to be somewhere over here, right? If I just start at the horizontal and move 40.6, I definitely won't be down here. I haven't gone far enough, okay? I have to go the full 180 from horizontal and then keep moving past 180, another 40.6 degrees. And so my actual direction of this particular one is going to be 220.6 degrees, because that's the direction of this particular vector. I had to go all the way from horizontal. So I started here and I went all the way around. The trig helped me figure out the 40.6, but the direction of it technically adds another 180 to it because I'm always moving from the horizontal. Here. Two vectors are equal if and only if they have the same magnitude and the same direction, all right? Magnitude and direction, V to Z. So over here they said V and Z. It does not matter that they're different places on the coordinate plane. They have the same length and they are the same direction. You'll notice V and U, while they have the same length, U is going another direction. So what's going to happen is my direction for this guy is going to be a greater than 90 degree angle, obviously here, and this is going to be an acute angle here. Make sense? Parallel vectors. Two vectors are parallel if and only if they have the same or opposite direction. All right, so direction now means degree. And so they gave the example V and W. So we have V and we have W. If you go from the horizontal, these are going to have the same direction, right? Because they are parallel. However, they gave the other example of Y. All right, Y is going a different direction, right? He's going to be that same angle plus another 180, but he's also parallel. All right, and so as long as they have same or exactly opposite directions, then they will be parallel. And you can see that visually, that even though Y is going a different direction from W, they are parallel. All right, they are parallel here. Does that make sense? So for this one, I would create actually the same triangle here. I would create a triangle like this, and I would create a triangle like this one. For W, I would not have to add 180, right? Whatever I found from here to there. But for this one, I would have to add 180 and find this angle. But they're still parallel. This is what I talked about when I talked about that symbol. All right, and we're not going to do a ton of these, just to show you really quickly. ABC, this is going to be a triangle, right? -3, -1, -1, -2. And -3, -3. So I have this triangle here that they have given me. And they are telling me to move it under a translation. And they have given me the translation in vector form. All this means in vector form is they are telling me how to move my X's and how to move my Y's. That literally just means 4 to the right, 3 up. So that is a notation for a translation, that instead of them verbally saying move this X number of units right, X number of units up, they can just write it in a vector form. And this form tells you, it's telling you to move every single point that direction. So they are saying move every point 4 units right, move every point 3 units up. So it's just a notation. We have done it. It's just how it's notated. Instead of it verbally saying it, it can actually give you your notation and tell you to do that translation. Make sense? Easy. All right, let's look at some combinations. Key concepts here. All right, to add two vectors, add the corresponding components. So if I have vector A, which consists of A1, A2, those 2 points there, and B, I can add them by just adding the corresponding points. So adding basically my X value, adding my Y values together. And then that would be my new vector. And so you can actually do a combination of vectors, which moves it more than one place on the map here. It says the sum of two vectors, this is a term you need to know, is called the resultant. All right, and then they give you this type of movement here. If I were to translate it once and then translate it again, I could translate it 2 times, or I could just add my translations and translate it once. This would be the resultant vector here. If I were to add these two, 5 and -2, add those, -1 and -6, add those, and then I could just move it once. The 3, -7, 3, -7. So all they did is they took these 2 movements from here to here and then here to here, and instead of moving it twice, they added the movements first and just moved it once. All right, resultant is when you add 2 vectors. Add 2 vectors, all right? Let's look at some word problems. We'll be done. The middle of page 501, scalar multiplication. All right, scalar multiplication we have done. And basically you did it for your bell work. I said do a dilation of 1/2. You multiplied all of your points by 1/2, and you got your new points. That is scalar multiplication, all right? So you can multiply a vector by a scalar, and you just increase or decrease the length or the magnitude of the vector. You don't change the direction. The direction will not change with scalar, but the magnitude or how long it is will change. Suppose a pilot begins a flight along a path due north, flying at 250 miles per hour. If the wind is blowing due east at 12 miles per hour, what is the resultant velocity and direction of the plane? All right. And so the resultant velocity is actually how that vector is where the new green one. So basically what they've said is he's flying due north, right? Which looks like this. Hopefully we all know what north is. Wind is blowing 20 miles an hour due east. All right, due east. Now what that creates is, that creates right here a 20. So we have 20 there. We have 250 here. And they want to know what's happening here. This is a right angle. There is a theorem that we have learned that when we have two legs of a right angle, we can solve for the hypotenuse. So how do I solve for the hypotenuse of a right triangle if I have the two legs? There we go. A squared plus b squared equals c squared, right? So my a squared, 250 squared, plus my b squared, 20 squared, equals my c squared. All right? So 250 squared and plus 20 squared, 62,900. Take the square root of that guy, and you will get your hypotenuse. All right, now you'll notice we don't have to consider the positive and negative here because it is magnitude, which is absolute value. So it's 250.8. All right, 250.8. In this case, if you were solving for the horizontal, you're going to do it a little bit differently than what they did it, okay? So they solved for the direction from due north, all right? From due north. So you would have to like flip this guy sideways because we're used to doing it from the horizontal, okay? And so if they wanted it how far off of north he is, they're just going to solve for this angle. They're solving for direction from his original direction. Normally, like for all the ones we've done it from the horizontal, okay? They are specifically asking, what is his direction from north, all right? So from north, his direction is just going to solve for this little angle. If they were just solving for direction overall and did not say from the north, you would solve for this angle right here, okay, from your horizontal. But since they said specifically from his original path, what is his direction now from his original path? You just have to solve for this little tiny guy there, all right, which is still going to be tangent. So I'm still going to say, well, the inverse tangent then of my opposite, 20, over my adjacent, which is 250. And you get about 4.6, I think. Yes, 4.6 degrees. So that's how far off he is from due north. If they wanted just direction, I would subtract that from 90. Why would I subtract from 90? Because this is my 90. I solved for just a piece of it. I wanted the rest of it. Okay, so I could actually subtract from 90 and get the direction from horizontal if I wanted.